Bismillahirrahmanirrahim. This video is from chapter number 14, Bode plot. I have several videos on Bode plot, but this one I thought will clarify some of the doubts that students might have. So let me discuss this. First of all, the definition of Bode plot. A Bode plot, actually the name is Bode plot, but generally in India, Pakistan, we call it Bode plot. So a Bode plot is a graph of logarithm of the transfer function. So any transfer function, we can plot it on the log scale. This is the frequency scale in terms of a log, and this is the amplitude scale in terms of log or dB. And just an example is shown here. This is the shape of the Bode plot, dB on the vertical scale and the log of frequency on the horizontal scale. Now let me just clarify, I'm just taking 4 or 5 examples of transfer functions, and we want to relate with the general equation, which is like this. So in the general equation, we will have a constant in the numerator and maybe at the denominator, just like we have 200 here or 50 here. Then we'll have simple j omega terms. So j omega terms, this is called the zero of origin function, and similarly, if there is a j omega at the denominator, this will be called pole of the origin. So just like here. Then the next term will be 1 plus something. This we will convert as 1 plus something, as we had shown in the previous slides, by dividing. So this will be a function like this. It will be in the numerator as well as it may be in the denominator as well. And then we might have a quadratic function or square function power 2. Now the numerator is called zeros, and everything in the denominator are called poles. Okay, now if this is the transfer function, we can very easily plot with the help of MATLAB, and just writing these 2 lines on the MATLAB, 2-3 lines, you get this plot. Now this is the magnitude plot and this is phase plot. Now when there was no MATLAB, then it was done manually, and so we got to learn that technique, so we understand basically what is the mechanism. So if we manually plot this, we'll have 2 points, 2 lines actually. One is the straight line like here at 0 level, and then at some frequency point, which is 30 in this case, it will slope down. And when we just curve it here, then this magnitude plot will be almost similar to what the computer has drawn. Similarly, for the phase angle, we'll have a plot like this. We'll discuss subsequently. And here also, if we curve the 2 ends, it will look like this phase diagram. So in this video, we'll be discussing how to plot these 2 curves. Now in the book, there is a summary table given, and many students try to skip this or have difficulty understanding. But this is very important. If you understand this, then you will have no problem in solving any of the Bode questions. So let me just go through this. Again, these values we'll use as a reference. First of all, we will plot the constant k. So constant can be any value, 0.5, 30, 100, or maybe 200 here, 50 here. So we just take log of that value, and whatever is in terms of dB, we plot it. This is our 0 scale, and this is the value of the constant. So this is the magnitude, and since constant does not have any phase angle, its phase angle is 0, so this will be the plot of phase along with the 0 line. The next we'll look into j omega plot. Okay, so j omega can also be j omega square, can also be j omega power n. So just for simplicity we are taking this. So its magnitude will be, or in dB it will be 20 log omega, and the angle will be j, and j we know is equal to 90 degrees, so angle will be 90 degree. So let's first of all plot this, and if we put omega is equal to 1, shown here, when we put omega is equal to 1, 20 log 1 will be 0. That means the amplitude curve will cross the 0 point. So this is one of the points that we have to keep in mind, that it will cross at omega 1, it will cross the 0 line. Number 2, what about the slope? Now the slope will be, it's called actually 20 dB per decade. That means if we move 10 times on this graph, that is from 1 to 10, then the vertical axis should be 20 dB. So this graph, this will be the slope of the graph, and so it is 20 dB per decade, and we can extend this graph all the way. So this was the magnitude. The phase angle will be, as we said, it's 90 degree. So this was our zero axis. We plot a 90 degree line for the phase angle. Now since this is at the numerator, this will have a positive angle, positive value, positive slope, and positive angle. And this is also called zero at origin when it is at the numerator, because the terms in the numerator are called zeros. Just opposite will be when we have j omega at the denominator, 1 over j omega, just like here or here. So this will be the pole at the origin. And the only difference will be that we just reverse this, we flip this down, and the slope will now be negative slope. So negative 20 dB per decade, and the angle will also be negative 90 degree. So this was the j omega term, and now let's see the third term, which is called simple pole or simple zero, which are something added with j omega, some constant, that j omega plus 2 or j omega plus 10. And as we had discussed, we will convert this into the standard form. So by dividing, we get in this form. Just taking common z1, if we take common, we get this term. So this will be our standard form. Now we'll take log of the standard form. So it is 20 log the standard form, and this will be called the magnitude in dB. Now there could be two scenarios here. If omega is very, very small, approaching 0, that means this term will be 0. So the net value will be 20 log 1. And 20 log 1 is equal to 0. So the magnitude will be 0 when omega approaches 0. So we can plot it like this. If this is the omega line or the frequency line, the magnitude is 0 when the value of omega is very less, approaching 0. The other option could be that the omega is very high, infinity. And when it is infinity, this term will become infinity, so 1 is meaningless. So we can say that the net value will be 20 log omega over z1, and we will plot this. As we had seen, this will be a 20 dB positive slope. So we plot it like here. Now this was our corner frequency, so it is moving away. It is almost towards the higher end side, or infinity we call. Now we have these 2 points, so we can add them, we can combine. Up to 0 we bring the 0, and from 0 we take this slope. So this will be our amplitude plot for a simple zero factor. Now for phase angle, we will recall that x plus jy, the magnitude is the square and a root, and the angle is tan inverse y over x. So same here, the phase angle will be tan inverse y over, this is y, over x is 1, so it will be the same value. So this will be the phase angle, and now we'll plot this. So we have plotted the magnitude, now we'll plot the phase angle. Three cases we'll consider. When omega is 0, this will be 0, and tan 0 is equal to 0, so this, the value of tan inverse will be 0. If omega is equal to z1, so this will be 1, and we know tan 45 is 1, therefore this angle will be 45. And finally, when omega is infinity, this will become infinity, and tan 90 is equal to infinity, so the angle will be 90 degree. Now to plot, we'll take a little bit of an approximation, and that approximation is something like this, that the value 0 will be from anything which is less than z1 over 10. Now this was the corner frequency z1. We go down towards 0 10 times. So z over 10 is our point before which the value will be 0. So this is 0. Then the middle point, when it is 45, no issue, it's continuing with the slope. And what about this point where it is 10 times greater instead of infinity? When it is 10 times greater than z, then the value will be 90 degrees. So we'll use this graph, this 90 degree, and this is 0, and this is the slope. Okay, so our final answer now we can, this was the magnitude for the simple 0, and this is the phase angle for simple 0. Now if there was a simple pole, that means it is on the inverted side 1 over this, then all we will have to do is just turn this, go to the negative side, so the negative 20 dB per decade, and this angle will be negative 90 degree. And finally, if we have a quadratic values, so like this quadratic equation or power of 2, then the slope will be double. So instead of 20 dB per decade, it will now be 40 dB per decade. And if there is more power than 1, then it will be multiplied by n. And the angle will, instead of 90, now it will be, because of the square, 90 plus 90, 180. So this is for the 0 of the quadratic factor, and the pole of the quadratic factor will be same, just opposite. Okay, so with this knowledge, now we'll solve an example. We have to construct the Bode plot for this function. So the first thing we need to do is convert this into standard form. So we take 2 common from here, and 10 common from the second one, and 10 and into 220 200 divided by 20 will be 10 j omega, this factor. Now there are 4 things to plot: this constant, this j omega, this pole, and the second pole. Now this is h, or in phasor form, we can write it in magnitude and phase angle form. So this is the magnitude form. We've taken magnitude of all the values, and then angles of all the 3 terms. Now angle of 10 is 0, but j omega angle is 90 degree. Angle of the pole terms will be negative 10 inverse omega by 2, as we calculated in the last slide. Phi will be negative 10 inverse this value, And similarly for the second one, negative tan inverse omega over 10. Okay, let's plot the now in terms of a dV, the values. HdV will be 20 of the constant, 20 log constant, plus 20 log j omega, and then when we come at the denominator it will be negative, so negative log 2 of the first value and negative 20 log of the second value. So this is the magnitude value in dV, and the angle remains same. We just write it here in terms of angle, same values. Okay, so this was the magnitude. Now let's see how to plot. First of all, we'll plot this constant. So this line is 20 log 10, which is equal to 20. So we've drawn a line at 20. Then we have to plot this value j omega terms, and we know that the j omega must cross 1. At omega 1, it must cross the 0 axis. So it is crossing 1 at the 0 axis. But how do we determine this? The slope, it is 20 dB per decade. So we go 10 times from 1, that is this point, and if we move up to 20 dB, that is the slope intersection point. So this is our slope line, and we can extend this toward the negative side, and it will touch here at negative 20. So this was the plot for the second one, and in the next slide now we'll plot these two. This was the first. Okay, now for the poles we know it will be negative slope. So we have two curves, there are two poles. One has a break frequency of 2, the other has a break frequency of 10. So up to 2 it will be 0, and then at 2 it will go down. So 0, and at 2 it will go down to negative 20 dB per decade. And similarly at 10 it will go down at the same slope, 20 dB per decade. So we have all the 4 plots. Now we need to add them to get the final result. And the result will be like this, but let's see how did we come to this point. Okay, let's mark this point here. You see, up before this there are two things. One is this constant line, and other is the upward going slope. Up to this point there is no change. So if we keep on adding, like here 20 minus 20, so it will be 0, so it will start from here. And then as we move at this point, the value of this line is 0, and this is 20, so 20 plus 0, so our red line is at 20. And similarly it will continue up to this point, same slope will continue. Now what is happening here, that there is another curve going down of the same slope, 20 dB down. Now this positive slope and this negative slope will cancel here. So what will be left is only the straight line. So our result will be a straight line up to the next change. So the next change is occurring at this point. There is another line going down. So these were already cancelled, only this was remaining, but now with this there is a line going down negative, so our result will also go down at the same slope. So this is our final shape of the result, and now we'll plot the angle. Okay, so this angle, and there's a little bit of a tricky, as we had already discussed. We start, or our 0 is before 10 times of the corner frequency, so 10 times of this. Now in our case, one of the corner frequency is 2, So it will start from 10 times of 2, that is 0.2. So 2 10 times 0.2, so our this point is 0.2. Before this it will be 0, and from here it will go down. So let's see. So at P10 this is going down, and it will continue up to 10 times P. So 10 times P1 is our 20, because this is 2, so 10 times 2 is 20. So up to this point this slope is continuing, and then it will become 90-degree flat. And now the third one, for this, the corner frequency is now 10. So 1/10 of 10 is 1, and 10 times 10 is 100. So we'll have the next line starting from 1, and it will become straight or 90-degree at 100. So all three we have plotted, and now we need to add here also. So this is our final shape. And how do we get? Let's see. This point, see, we have 90-degree and we have nothing here. This is 0, so the main result will be 90-degree. Now next, where is it changing? Up to this point we have these two, so that means 90-degree and some angle going down. So our slope will go down with the same shape like here up to this point. Then there is another slope now going down, so the slope will double. So here you can see this slope should have gone like this here, but now it is doubled, and this will continue up to this point. Okay, now here this line is ending, this is becoming 90, so 90 minus and 90 plus will cancel, so only one slope, this slope, will continue up to this point. And at this point now we have 190 plus and 2 minus 90s, so this will be minus 90, the final answer.